After the speed of light had been shown to be the same in all reference frames, it was apparent that we needed to revise the fundamental understanding of how observers in different reference frames experienced the universe. This may seem like a daunting task, but was done by Einstein in 1905 by considering just a few very simple thought experiments. The first of these thought experiments goes like this. Consider Isaac standing on some planet while Albert speeds by with a velocity v in his spaceship. In Albert's spaceship, there's an experiment set up consisting of a laser beam pointed at a mirror in the direction perpendicular to the ship's motion. When the laser fires, it starts a timer. The laser pulse then bounces off of the mirror and returns to the laser, at which point the timer stops. Isaac is also equipped with a timer that starts when the laser pulse is fired and stops when the pulse returns to the laser. Distances measured perpendicular to the direction of motion should be the same in both reference frames, since there's nothing different between the two frames in this direction. So if the mirror is located at a distance d over 2 from the laser, this distance has to be the same in both reference frames. We also know that the speed of light, c, has to be the same in both reference frames as well. When the experiment is conducted, the time that Albert measures is just going to be the total distance the light travels divided by the speed it travels. We can write this explicitly as the change in time for Albert is equal to d over c. However, Isaac sees something very different. In his reference frame, he sees both the mirror and the laser moving. So when the pulse is emitted, it travels the same distance as measured by Albert in the perpendicular direction, but it also travels some distance in the direction parallel to Albert's motion. The total distance it travels in the parallel direction will be the distance that Albert's spaceship has traveled in the time it took for the light to return to the laser, given by v times the change in time measured by Isaac. We know that the total distance for the round trip of the light pulse has to be c delta ti, and so the distance for just one leg of the trip is half of that. Looking at this, we can see that we can form a right triangle by splitting the path in half. Then, we can relate the two legs of the triangle to the hypotenuse through the Pythagorean theorem, which gives c delta ti over 2 squared is equal to d over 2 squared plus v delta ti over 2 squared. Rearranging for d, we find that d is equal to the square root of c squared minus v squared times delta ti. But since this is the same distance that Albert measures in the perpendicular direction, we can substitute it into the equation for the time measured by Albert, which gives delta Ta is equal to the square root of 1 minus v squared over c squared delta Ti. This expression may not seem very special, but it has a lot of information in it. First, we can see that the amount of time measured in the two frames is not the same. In fact, since we are subtracting the v squared over c squared term, the time measured in Albert's frame is less than the time measured in Isaac's frame. In other words, time moves slower in Albert's frame than in Isaac's frame. Albert will not age as fast as Isaac will. This phenomenon is known as time dilation. Another important observation of the time dilation equation is that the value of v squared over c squared is subtracted from 1. Since an imaginary time doesn't really make sense in this context, the speed of light is acting like a speed limit, since the ratio of v over c can't be greater than 1. So we have come to the conclusion that nothing travels faster than the speed of light. A quick comment on notation. The factor of square root of 1 minus v squared over c squared shows up a lot in special relativity, so we give it a special symbol of 1 over gamma, or gamma equals 1 over the square root of 1 minus v squared over c squared. This is known as the gamma factor. It is also worth pointing out that for speeds much smaller than the speed of light, the gamma factor just reduces to 1, and you obtain the results of Galilean relativity. In this case, the time is never different between reference frames. So, from this one simple thought experiment, we have already been able to come to some pretty groundbreaking conclusions. However, Einstein did not stop there, and there are many more thought experiments to explore and new physics to find.